the recording started. There we go. So we're looking at this thing here. I realized afterwards that my example here has, let me make this a little bit bigger so you can all see it. It has group that's starting 0, 1, 2, 3. Group in your homework, section 1, is coded 1, 2, 3, 4. So I did not mean to confuse you. It's coded in a different example for my next class as 0, 1, 2, 3, and that's why it was at the top of my head. But this actually brings up a point in terms of your own strategy when you're doing this sort of coding and trying to put the new parameters into the model and make sense of the results. This is a very generic way of doing things that is not likely to help your working memory overload. So if I were to code things, say group 0 versus 1, group 0 versus 2, like I've done here, when I see those labels again on my output, I have to then go, okay, who is group 0 and who is group 2? And that's an extra step that makes it harder to keep track of what's going on than is what needs to be. So in practice, what I would encourage you to do is to use some kind of abbreviation for these groups that makes sense to you so that you can immediately recognize it. So for instance, in your homework, the 4 groups that we're dealing with are different training groups in evaluating effects of mini golf training versus regular golf training. So the first group is the control group. So instead of saying like group 0, I might say, C for control. And then the next group, rather than saying it's group 2, is M for mini. Something like that, to where when you see the words in your output, you don't have to take the extra step of trying to remember how you constructed these things. By the way, is anybody curious about this story with the mini golf and the regular golf? So all of my homeworks are based on real life experiences, for better or worse. You got to read about fits thrown and pleases heard in preschool life in your previous work. This story with the golf came from a visit to see my husband's family. His family is in Sacramento, California. That's where he grew up. Over Christmas, probably 10 years ago, something like that. And my husband is a relatively easygoing guy. And one of the things that we did while we were there with his family, he has 2 sisters, is go play mini golf. And so I was expecting, okay, we're going to go play mini golf. It'll be fine. No, it was like cutthroat mini golf. Like they took this shit seriously. And he was talking all kinds of trash about his mini golf game. And it was just really like, where did this man come from? I've never met this version of you. Because I don't care. It's mini golf, right? So then I started thinking about, like, well, what would be the things that would be important in optimizing your mini golf performance? And that also brings up conversations I've had with my dad, who claims that he's not good at mini golf because he plays regular golf and there's interference in the skills that are involved in each. So a combination of those 2 life events created the training program example that you are playing with right now. So the question is, if you train in both kinds of golf, does your performance decrease relative to training in the one that you're being evaluated in? So one catch with this, and I put it in bold font, lower scores is a better performance. Okay, so there's some of the questions where I'm asking about a significant benefit versus a significant cost to performance. If the group has a lower score, that is a significant benefit, okay? Because you want lower scores are better in golf. And I know that that's potentially confusing, but there are real life outcomes where less is better, right? Disease prevalence rates, um, disruptive behaviors. There's lots of types of outcome where the best thing that could happen to it is to have a lower score. So this is one of those outcomes phrased that way. So are there
Can I
any,
ask a question?
I
Yeah,
was just
about
going to
that.
ask, yeah, are there questions, please?
Well, so I was confused because I think it was like was it 18? I can't remember. I was looking at it, but the lower is lower just compared to based on what you get results, or is it lower compare like are there like categories of low, medium, high? Like what's low, basically?
Um, I have question 18. I don't know that that's that one. It's the
No,
slope
I
for
mean
control
the
versus
number
regular.
eight. I meant the number 18.
The number 18.
There was something about wasn't there something about the number 18, or am I thinking? The question
Um,
anyway, is about low in general, just low.
okay. Yeah,
So
so
it's
if
low, zero. Are you talking zero is lowest possible?
not so that was in example 4. I had a 3 group example that was low, middle, upper. In this
Hmm.
example, it's given to you at the top of the syntax file. So let me
Okay.
pull that one of those up real quick. Um, there is no such thing as real quick when my computer's working this hard to keep everything going, but here it is. So this is one of the starter syntax files. The variable that you're working with right here is
Hmm.
group, and 1 is control, 2 is training in mini golf, 3 is training in regular golf, and 4 is training in both.
Oh,
So
okay.
those
So
are
number of,
your,
yeah, I'm getting 18 from the number of strokes on the 18-hole mini golf test. So
yes,
at number of strokes over the whole, like 18, like, so we're predicting the number of strokes, right? Isn't that
yes. So the
based on your experience, group experience?
based on, yeah, which group you're in, how many strokes did it take to complete the 18-hole golf course? That's your
So
outcome.
18 would be the lowest, or no?
Yes, it should
Okay,
be.
18.
Although it's possible that the way I simulated these doesn't exactly align to that because I was using a normal distribution to generate the residuals, so there may be some funkiness with that, but yes, in theory, 18 would be the
18 would,
lowest.
okay, okay.
Okay, so
Thank you.
sure. On the questions that ask about lower versus higher, for instance, those I mean just straight like which number is higher and which number is lower. There's no additional calculus required on that. So which group had a higher score, which group had a lower score, and then what does that mean? There was a benefit of training if the group that's of interest had the lower score, or there was a cost of training if the group that was of interest had the higher score. So each of these questions is relative to something. So for instance, on this line right here after question 57, it says relative to the average number of strokes in the control group. So starting there, the comparison group was higher or lower. And all of these zeros, once you complete the computational section, will be pre-populated with the answers that you had up above. So that can help you follow your own logic as you go through and reconstruct your results. So in practice, when you're evaluating these sorts of grouping variables, it is critical to indicate who's higher and who's lower, not just there's an effective group. So it's worded this way, but you can still think of it as a positive slope versus a negative slope. It's just a little more intuitive if you're phrasing it as this group is higher as opposed to the slope was positive. So are there other questions on this set of questions in section 1? Okay, in section 2 then, this one is relatively short. All I'm asking you to do is to fit a quadratic effect of a predictor of enthusiasm. And enthusiasm, by the way, this is another joke. I don't know if you caught this. In my lame sense of humor, the enthusiasm, mini golf enthusiasm scale with the acronym MGUESS. Because it's like, do you want to go and play mini golf? Guess. It's fine. That's my level of enthusiasm. Like, okay, if I have to, sure, we can go do this, but I'm not taking it seriously. So the MGUESS scale is already scaled such that 0 is near the mean. So in this example, I asked you to leave it uncentered because 0 was already a meaningful value. So I'm just looking for you to fit a model that has both the linear effect of enthusiasm and the quadratic effect. So the model has to have both slopes in it to be correct. When I say linear effect, that's just putting in enthusiasm as a predictor like you normally would. It's like the default version of a slope is a linear slope. And then do you remember how to get a quadratic version? In SAS, it's an asterisk between the two, and in Stata, it is a hashtag /#, depending on which generation you're from. And so then I'm just asking you to answer questions about that model without any of the extra estimate or LinCom statements required. Those are an advanced concept I wanted you to have an example of, but that I'm not asking you to be able to master at this time. And then just a few questions about that. So are there any questions on section 2 for those of you who've started working on this? Okay, last but not least, I wanted to give you some help with section 3. Would that be okay? A little bit of assistance? Oh, emphatic nodding. Okay. Yes. So the idea here is to give you some practice coding piecewise slopes. The idea that you would divide a predictor variable into different sections and to fit a different slope through each section. So my hand gesture is trying to like have sort of two sticks put together, right, in various forms, is a way to approximate a nonlinear relationship. And I'm asking you to fit one slope that goes from experience 1 to 4. So this is an ordinal variable that we're pretending is interval, and experience 4 to 7. So does more experience help amongst people who don't have that much experience is the first slope. And then does more experience still help amongst people who have a lot of experience? So that's what I'm looking for, is just for you to code up two slopes. And I thought it might be helpful for us to build the table, and then you can take a shot at writing the code that goes with it. So let me get this a little bit bigger here. I'm adding on to the thing that we started before. So experience is the original variable, and it is coded like this. Okay, can you all see where I'm typing? Okay, let me blow it up just a little bit more. That way it shows up on the recording more clearly as well. Okay, so I am naming my first slope experience 1 to 4. Let me put the word in there. Experience 1 to 4, and the second slope is going to be experience 4 to 7. Okay, those are the two new columns that I need to predict to be able to divide up the effect of this variable into two piecewise linear slopes. Now the instructions told you that I want experience level 1 as the model reference. So because I want experience level 1 to be the model reference, what goes here? Yep, zeros. So another way of thinking about that is experience level 1 is where I want my intercept to be. Reference point and intercept and you are here sign, all of those things mean the same. So if I want experience equals 1 to become the model intercept, that means I need to code my new predictor variable 0 so that the intercept is the expected outcome when all the predictors are 0. The intercept will become the expected golf score for those who have an experience level 1. So that's always the first step. Where do you want your intercept to be? Zero out that spot. Now the second step, I need to build a slope that tracks the change in experience moving from 1 to 2 to 3 to 4. So if I've just coded experience level 1 as my 0 point, relative to experience level 1, how much more is experience level 2? 1. How much more is experience level 3 than experience level 1? 2. And then 3. So far, this looks the same as if I had just told you center experience at 1. You would build those 4 values by having a new variable, experience 1 to 4 equals the old variable like that. So far. But we'll have to modify this in a minute. So let's do the other side. I want this slope to capture the change in experience as we go from 4 to 7. So up to this point, it's not relevant. It's not activated yet. So I'm going to zero that out. Now I want it to turn on after 4. So relative to 4, how much more is experience equals 5? How much more is experience equals 6? Yeah. So I've got one slope that captures the change as you go from 1 to 4. And then the idea is that the second slope then captures the change as you go from 4 to 7. Questions on just that much? Now, what goes here is the tricky part. The instinct is to think 0, right? Because you want it to shut off. But in this case, if I put a 0 here, what would happen is that the prediction would go all the way back down to where it started. And I don't want it to go all the way back down, I want it to leave off. So rather than putting 0s here, I'm going to put 3s. The idea is that if experience is helpful, that should mean a negative slope. And then I want that slope to shut off after experience equals 4. I don't want it to go all the way back to where it started from. Because then the second slope picks up where this shut off, and it can be whatever it wants to further capture the effective experience from 4 to 7. So building the code that goes with this table then would be if experience is less than 4, then make these. Otherwise, if experience is greater than 4, then make them this way. So it's the same conditional logic that the piecewise slopes for education were created with, just with only 2 slopes to be created instead of 3, and a different hinge point as it's known. Rather than 12 years, it'd be 4 years. So this statement will have to be qualified. In SAS, it would be something like, if experience is, let's go with less than 4, then so something like that would get me that much. If experience, the original variable, is less than 4, then make my new variable a function of experience minus 1. Otherwise, let's see, if experience is less than or equal to 4, the other variable, hey, come back. Okay, it's not going to let me edit. Goodness, that's why I'm in the wrong cell. There we go. Experience 4 to 7 is going to be 0. Scroll back over. There we go. So I've got that much with the 2 statements.
What is the LT? That's lower than?
Less
No,
than.
that's less than.
Mhm.
So you have the same thing if experience is less than 4 in both of these.
Mm-hmm. So in SAS, you can combine them with a then do and put them both in the same line. In Stata, you cannot.
Okay.
So it would be 4 statements in Stata, but just 2 statements in SAS, or you could write it out sort of this longer way where each one is a separate condition, separate creation by the condition.
Thanks.
A quick
Sure.
question.
Yeah.
So I don't understand. So if column like 5, 6, and 7 are 3, how does that match the first 4 zeros in the second one? Like if they're supposed to meet at this same point, they're not though. So I don't understand.
So I am coding this much of the table rather than this one and that one. So if experience is less than 4, I'm making one variable that is experience minus 1, and then I'm making the second variable that takes a value of 0.
Okay, so then it's coding the 0, 1, 2, and 3 that reaches 4, and then in the other one, since it starts at 4, it's 4, 1, 2, and 3. Oh, okay.
Yeah, it's still starting at the same place. It's making the second column rather than continuing the rest of the same column.
Oh, okay, makes sense. Sounds good. Thank you.
So then if we do the same thing for the other half of it, I'll do greater than or equal to 4. So that way 4 is inclusive. So now the first one is going to be what? What goes here? Yeah, this
Should
is a
it
hand
be,
signal one.
should it be experience equals 3?
In this case, it's not conditional on what experience used to be. It would just be 3 regardless.
Okay.
And so you can just type 3.
Oh, okay.
The next one, though, is conditional on experience because it has to change as a function of what experience was. So what mathematical function do I need to make it change like that? Yeah, this one is going to be a minus 4 because that is how those numbers would be created. The original experience minus 4 would give me a 0 at 4, a 1 at 5, and so on. And so once you get a chance to build the predictors, then you would put them both in the model at the same time, and they would each track the effective experience within their section of the variable. And the last thing that I'm asking you to do is to compare the two slopes. And there's multiple examples of how to do that in the code as well. So you just need to find one of those and answer whether or not having this variable have a separate slope from this variable is necessary. There's a significance test that you can use to determine that. Okay, other questions or any of that you want me to talk about more or again? So this is not due until a week from Monday, so we've got some time to work on it. I'm happy to help troubleshoot if you run into error messages. It's helpful if you send me screenshots of whatever code and what happened with the output. Those I can look at on my phone while I'm sitting with my son, for instance, and I'm not at my computer, versus if you send me like the full files, then I have to go to my computer to open them. So the screenshotting is very effective as a way of showing me what you've been doing and what may have gone wrong. So give it a try and let me know how it goes. And I will put this up on today's class since we added to that. There, saving. All right. Anything else before we change gears?
Yeah, I'm sorry. I just don't understand why we're doing LT and then GE also.
So LT is less than 4 and GE is greater than or equal to 4. So another way, I'm in the habit of writing these out but I think an equivalent way of writing it would be like this with less than signs and then greater than or equal to. I think that works in SAS. I know it works in Stata, for instance. The reason that we have to have that is to make sure that 4 gets included. Otherwise, if we had less than 4 and then greater than 4, 4 would not meet any of the conditions, and so people who had a 4 would not get the new predictors made. This way, 4 is inclusive in the second set.
Okay, so then the first two lines are for like column B, and then the last two are for column C.
No, the first 2 lines are for this section of both B and C. So if the original experience column in A is less than 4, then I'm going to make each of these new columns. So the first line makes the column B, and the second line makes column C.
Okay. Okay, I understand now. Thank you.
Yeah, you're thinking of it vertically, and I went horizontally.
Yeah, exactly.
So, yeah, if if it makes more sense to you, you could rearrange these things like that, and then that would be the way that you were seeing it. Like if you do all of column B first, and then you move to column C.
Thank you.
So, and either one works. So whatever makes the most sense, that's the right way. All right, other questions?
Yeah, the repeating 3, that's for the point where we want to switch lines, right? Where we're going to go to another slope.
Yes.
Okay. So generally, if we want to switch lines like this in other situations, we do this.
Yes.
So, okay.
Yeah, in this case, because we're working with integers, you can just put in the 3. In other cases where you would potentially leave off at a different value, you'd have to refer to a variable in the data set rather than as a constant. That would happen, for instance, in longitudinal models where people might be at a different time, like at the third occasion might happen at a different point for each person, in which case you'd have to find out which point that was and hold it equal to that point. So that's a slightly advanced version of this, but the logic you can apply to piecewise slopes more generally. Okay, others? All right, then we were looking at, let me see here. We were doing the 3-slope version of this, and we didn't get a chance to see how to make SAS and Stata do it, so I thought that that might be a good place to start. So I am on example 4, page 11. Make this a little bigger. There we go. All right. Do you want to make SAS and Stata do your bidding? Well, let me put it this way. Would you rather hand calculate things or make SAS and Stata do your bidding? Yeah, no, boo to hand calculations. Yes. SAS, please. In addition to hand calculations being annoying and tedious, they are very bad for reproducibility, which is the magic word these days. You want to make it so that some other person could take your files and perfectly recreate all of the things that you did and all of the conclusions that you drew. And so having as many things happen through the program as possible makes it more likely that someone would be able to follow your work. So it's important in addition to being less annoying. So in this example, I have done additional things here that I wouldn't ask you to do in your homework, which is generate descriptive statistics. So I didn't ask you to do this again because homework 4 was already long enough and because you got a chance to practice this. So you did this sort of thing in your first and second homeworks, right? You learned how to generate means and variances and tables of categories of frequencies and whatnot. So in life, though, as you're trying to think about what would be the best way to represent the effect of a predictor variable, step 1 would be to figure out what kind of predictor it is. And so knowing, for instance, that I have this scale of years of education that goes from 2 to 20, that can help me think about how I would code it in the model. And so in this case, because years of education correspond to boundaries that go with degrees, having a single effective education doesn't make a lot of sense because one more year of education doesn't get you the same impact if it's going from, say, 9th to 10th grade versus 11th to 12th grade. So the distribution of the predictor, as well as what I know about it theoretically and how it should affect my outcome, then leads me to choose how I'm going to represent this variable in a model. So this is a histogram showing years of education. As you might expect, there's a lot of people who report having 12 years of education. Most of the people in the sample, though, are relatively well educated, not as many people down here. And here is a plot on the right of the means by education. So we looked at this last time in the PowerPoints. If you're interested to see how I made this picture, there's SAS code online with which I did that. But what we're trying to do then is figure out a way to follow that black line. That black line describes how the mean education at each unique level is related to the outcome variable of annual income. So this is the type of trajectory, the type of functional form that we're trying to mimic. And the way that I'm choosing to do that is to carve it up into these three pieces. What is the effect of education for those who haven't finished high school? What is the bump you get of finishing high school? And then what is the effect of additional education beyond that point? That's what we're trying to fit. And so I just updated this to paste in the table from the PowerPoint because I thought it would be helpful for us to understand the coding. Since I just did SAS in the previous example, I'll focus on Stata to start with here. So in this example, I'm building 3 slopes. So I want 3 new blank columns. That's what the dot means, it's blank. The reason to do that is to make sure that I don't inadvertently assign values to somebody who has missing information for education. So that's why I'm starting them out blank and then only filling them in if they meet the criteria for what education level I have for each line. So that I'm filling in then selectively these 3 columns, less than high school, graduated high school, or over high school, if people meet the condition at the end of each line. So if education is less than 12. So I am filling in the first 4 rows of the table. I'm moving vertically across the columns. It's education minus 11 gives me what the first column would be. So 11 is my reference intercept centering point. And the other columns are zeroed out for people who have not yet graduated high school. And then I'm filling in education greater than or equal to 12. So the 4th through the end of the table lines, 0 for the first column, 1 for the second, because the job of the second column is to track the impact of graduating high school, but no more. So if we look at the pattern in here, the first slope shuts off after 11, and it shuts off at whatever value it left off at. So that's why those are zeroed out, is because 0 was the last one. Likewise, the second column, the last one was the 1 that you would get if you were education 12. And so it shuts off at the 1 because that's where it left off at. And then the third column picks up after the second column shuts off and indicates the effect of each additional year past 12. And so that's why it's education minus 12 needed to complete the last column. And the same happens in 2 lines of code in SAS, also moving horizontally, because SAS allows you to have this then do end in which you can build multiple variables that meet that selection criteria simultaneously. Stata does not allow you to do that, or at least I was unsuccessful in finding how. So SAS is making all 3 columns simultaneously for people with less than 12, and then all 3 columns simultaneously for people with greater than or equal to 12. Okay. Questions? Move this up a little bit. So we talked about this last time, but it's sufficiently complicated that I thought it would be useful to go over it. Are there anything else about the coding here that I can help you understand? Or do you feel like you've got a sense of what it's trying to do? And that was funny for some reason. I'm not sure why that was funny, but it was. Okay. So here's the result then. I'm putting in all 3 new predictors into the model. So here's SAS, and here's Stata. So note the original education predictor is not in here. The original education predictor was only used to create my 3 separate new predictors, and my 3 new predictors are what go into the model. And they only have the interpretations that I'm giving them if they all 3 are in there at the same time. They have to work together to describe the overall trajectory. So the model is directly going to give me a test of whether each of these 3 predictors has a significant slope, whether education has an effect in predicting annual income for each of the 3. Another thing that I am asking for, a homework question, is how to test differences between the slopes. And this looks a lot like the same coding pattern that it took to get differences between the non-reference groups. So if I return back to my spreadsheet for just a minute here, the part that we worked on last time, nope, there we go. The lines for the implied slopes, they have a pattern to them. So for instance, for group 1 versus 2, it's the slope that would distinguish group 1 with a minus sign, and then the slope that would distinguish group 2 with a plus sign. So this right here is what I'm focusing on. That -1, 1 pattern gives me how group 2 differs from group 1. Likewise, the -1, 1 pattern here gives me how 3 differs from 1. And then the last one here gives me how 2 differs from 3. So the one that you want to come first gets the -1, and the one you want to come next gets the 1. So -1 is like the reference within each of these statements. The same is true in this little piece of code right here. There we go. Now we can get both versions on the screen at the same time. This code is contrasting each pair of slopes that are adjacent to each other. So I'm comparing the effect of less than high school to the effect of graduated high school. And I'm also comparing the effect of graduated high school to the effect of over high school. And so this is something I'm asking you to practice in your homework as well. So when we see the results, I think it will make more sense why one would want to do this. But this is the execution, how you can compare the effect of the slopes that are already estimated as part of your model. Okay, are you ready to see the results? Yeah, all right. First thing, right here, this much. In English, as much as possible, what do all these numbers tell me? Why would I stop at this table and look at it? And the answer might be because you make us. But why would I make you would be the follow-up question. Overall model? Yeah. What am I trying to find out here with these 2 tables? What about my overall model? Those of you who are eating lunch can type. You can still participate. Cheers. If it's the right one to use, if it can predict reasonably, if the slopes collectively explain the variance, yeah, I'll take all of those. Right one to use to me sort of implies there's a comparison. So I think that could be true if you're deciding, say, whether you need 3 slopes for education versus 1 slope. This tells you how good the 3-slope model works. So yeah, explained versus unexplained variance, if we can predict reasonably, yeah, I think all of those things work. The idea here is the generic, like high level, what is it, 50,000 square foot view of the research question. Does education predict income? Like that's the question. These tables that I've highlighted say yes or no. Thumbs up or thumbs down, does education predict income? Because all that's in my model right now is education as a predictor, but it takes 3 slopes to capture the effect of education as a predictor. So if this F value right here, that's my test statistic. That is a ratio of information captured by education to information left over. And each of those sources of information has been weighted by how many slopes it took. So information per slope captured relative to information left over per slope not yet added. So 47 yields a significant p-value. So alpha 0.05 is my cutoff. This p-value is less than that. I would declare yes. It is unlikely to find slopes this large if the null hypothesis of 0 slopes were true. So we would say, yeah, the model is significant. More specifically, the model significantly predicts income. There is a significant correlation between the income level that is predicted by your education and the real income level that you have in the data. And the square of that correlation between predicted and actual income is my R square here. So R square is an effect size for how good your model is at predicting the outcome variable. So 16.4% of all of the reasons why some people make more money than others is because of their education. That 16% is significantly greater than 0 because that is what my F-test is telling me. So the model works. The model works in that I have significantly predicted my outcome variable with the terms I have included in my model. So far in each of the examples that we've seen, it's been one predictor conceptually that's been in the model. So before we had, say, 3 groups, and that was one variable for your working class. This is education as one predictor with 3 slopes. The next example is going to have like 4 or 5 slopes, I think, to talk about ordinal differences between levels of happiness. Starting next week, we're finally going to get to models that have more than one conceptual predictor, each of which may have 1 or more slopes. So to pit predictors against each other, so to speak. But for now, they're working together. So yeah, this sort of gives you the global picture of what's going on. Does education predict income? Yes, significantly so. Okay, how does it predict income? Do the pattern of associations correspond to the way that we would think about them? We haven't talked about hypotheses per se, but generally speaking, when you form a research question, it's because you have an inkling as to which way it's going to go, right? More education should relate to more income. So we would expect these slopes to be positive. Is that what happened? So we're going to drill down into the more specific results that this table gives us. These are the fixed effects of your model, and there's 4. There's beta 0, the intercept. That's always there. That's the intercept that gives you the mean of y. The question is, what else besides beta 0 did you put in your model? And that's these 3 slopes. So the first column is what's known as the slope estimate. It's labeled coefficient in Stata. By the way, if you hear the phrase point estimate, that's synonymous. Point estimate is sort of a stats term for the idea that it's one number, but the error around the number is conveyed by the standard error. Do you guys remember what a standard error for a slope tells you? You'll get a chance to answer that like 57 more times before the semester is over. So you will know by the end of the semester. But generally speaking, a standard error tells you how far on average the sample whatever is from the population whatever. So you just have to fill in whatever is in the current context. By the way, the stats term for whatever is parameter. That is a generic term for whatever the thing is you're trying to find. So yeah, the whatever, the thing, or the parameter, any of those works. So in this case, it's how far off on average the sample estimate of the slope would be from the population estimate. And so this confidence interval at the end here is 2 standard errors roughly around this point estimate right here. So if I take my estimate and divide by the standard error, that gets me my t column. T is a test statistic for an individual slope. So if you're only testing one term, you can do so with the t. And this t is minus 0.45. So what that's telling me is that my obtained slope of minus 0.27 is like a half a standard error away from the null hypothesis of 0. So in other words, it's well within what you would expect a normal sampling variation. Normal sampling variation is like 2 standard errors on either side. And that corresponds to a non-significant p-value. So the probability of finding a slope of minus 0.27 or larger, if the true slope were 0 in the population, the probability of finding what we found is about 65%. So because that p-value of 0.65 is nowhere near our alpha of 0.05, we would say this slope is non-significant. So the direction of it is negative given the sign. So non-significantly negative. So putting that into context, what does less than high school capture as a variable? It captures the effect of education in people who have not graduated high school. So like within that sort of subsample of your data from 2 to 11, the more years of education you have, the lower your income is actually predicted to be. So this is backwards. But we might say, well, it's actually kind of not different than 0, so we can just call that 0 and say education really doesn't matter if you don't graduate high school. If you do graduate high school, what happens to your income? Up by about $4,700, which is 2.5 standard errors away from the null hypothesis of 0 slope, and significant. So we have a significantly positive slope. For moving from education level 11 to 12 is expected to get you another $4,700. And then the last one. So this is among people who have at least a high school education, so 12 up to 20. In those people, every year more educated you get yourself gets you another $2,100. So those of you who want to stay in school forever, this model suggests that would benefit you, right? Stay up into 30th grade. You'll make yourself a millionaire in no time. And I'm being facetious, but I'm also trying to make a point. This is a linear model. Now, it's 3 different linear slopes, right? I got to do my hands for the different sections. But the last one says that predicted income just keeps going up and up and up and up and up indefinitely, right? We know that that's probably not going to work. So in practice, linear slopes may be unreasonable for certain kinds of constructs. And without even looking at what the results say, I can look at this picture and say, yeah, actually a single line through that 3rd section doesn't fit very well. I would need some way of explaining that there's diminishing returns the more education that you get. Okay. All right, how are we doing? So then the extra pieces. So I have here a table of extra linear combinations. These are the results of my estimates or my lincoms. What are they telling you? So what if reviewer 3 comes along and looks at the results of your model and says, I think it's ridiculous that you put 3 slopes in here when everybody knows that there should only be 1 slope. I recommend that you see these references for models that have fit only 1 slope because that is correct, and I am in no way related to the authors of these references. Yes, that happens. I'm only exaggerating a little bit. Like, you may as well sign your name if you're going to make me read your Vita, okay? That's the fair thing to do. And in fact, if I'm going to, like, okay, you really need to read my paper, I will sign my name and just admit to being that level of douche, right? I'm going to admit to it. But let's say reviewer 3 has an opinion about your work and they want you to only have 1 slope instead of 3. The best way to argue with any reviewers is to give them data, not opinion, but data. So I am going to make a hypothesis test as to whether or not these slopes are different from each other. So the hypothesis test that I have highlighted right here is each slope against 0 specifically. I am asking, is this number that was estimated at minus 0.27 different than the slope that was estimated at 4.6? Are those numbers the same or not the same? And so the first result, that estimate of 4.95, that is the difference between those 2 lines. The grad high school slope is 4.95 more positive than the less than high school slope. So the effect of education is bigger in people who graduated high school than in people who did not graduate high school. And I've got a p-value down here to prove it. So you can think about contrasting these slopes against each other as a justification for whether or not a piecewise model is necessary. Because if we're doing our sticks here, right? Like if I have a model where the 2 sticks are estimated like this, you may as well just put 1 slope through the whole thing, right? It's a question as to whether or not you need the 2 sticks or whether 1 suffices. And so the first test here is working on the first 2 slopes where there's no effective education and then there's a bump for getting a high school degree. And these 2 slopes are different. And then I did the same thing, contrasting those 2. Oh, and lo and behold, reviewer 3 may have a point. I hate it when that happens. Even though the first slope is 4.7 and the second slope is 2.1, the p-value down here is telling me those are not significantly different from each other. They are each significantly positive, but they are not different. So in theory, I could have put them together and drawn 1 line that goes from 11 all the way up to 20. So they may have a point with the second half of the trajectory. But if I were going to try to publish these results, I wouldn't have stopped at just a linear model for this part. I would have tried to do something else to make the third part fit better to begin with. But I decided to
Lisa?
here for the example. Yes.
So when you're testing the differences between the 2 slopes, I'm assuming you're just basically testing around the breaks, right? So it wouldn't be appropriate to test, not having a high school diploma with the people who are going on for higher education. You're kind of testing around the breaks. Is that accurate?
That is what I chose to do. Mathematically, there's nothing that stops you from doing what you just said. I would have a harder time justifying it as something I'd want to know.
Mm-hmm.
But in theory, you can compare any 2 slopes.
And then following up with what you were talking about, trying to fit that later part, what happens when you run into an instance where, like, certain breaks are significant, but like one in the middle isn't, would you just then create a slope for that middle one?
On something like that, I might argue to keep all of the slopes, even though it's not the most parsimonious representation, because it leads to the clearest interpretation.
Got it. Thank you.
Sure. So, like, if I would leave this in here, for instance, if I were reporting this model, even though it's non-significant, and people would say, well, if it's non-significant, you don't need it. I need it to make the point that anything below 11 basically doesn't count. Like to tell that part of the story, leaving it in the model makes that clear. So I would be hesitant to lump things together that muddy the interpretation of what each of the slopes means. Thank you for the question. All right, other questions on these findings?
Yep, I have a question.
Please.
So for the first slope comparison, which goes from, hang on, 2 to 11 versus 11 to 12.
Mhm.
So we already know that 2 to 11 is not significant, right?
Mhm.
Shouldn't we not compare it then? Because we don't know if it's like, if the slope, what would the interpretation be here? That we don't know that the slope is different from 0, right? For the one that's not significant. So I was thinking, I mean, this is just my own thinking. If I didn't like watch the lecture or anything, I thought on my own. So shouldn't you stop there? Like, why would you compare it to another slope? Because we don't even know if it's different from 0.
It's a different question whether it's different than 0 versus if it's different than another slope.
Okay. So we can test both those things separately. I mean, one doesn't depend on the other.
I don't think they do. 0 is a
Okay.
reference point for a hypothesis test. But you could just as easily engineer it to say, well, reviewer 3's research group found a slope of minus 0.5, and I want to know if my group's research slope is different than what they found, right? You could engineer any kind of is my slope different than something else that's of interest to you? And in the meta-analysis literature, for instance, if you're going to compare combine results from studies that are all looking at the same phenomenon, one of the things you try to do is to predict why one study found a different result for their slope than another study and try and figure out what makes the effects different. And so steps like this are demonstrating that there might be a difference between slopes to begin with. So I don't see those as logically inconsistent because they're answering different questions.
Yeah, I guess. Yeah, I'm thinking. So we couldn't tell if the first one was different from 0, but we can tell that the second one is different from the first one.
Mm-hmm. And the second one is also different than 0.
Yeah. So maybe it was just too small to detect, but the second one is different from it.
Mm-hmm. And okay. Keep in mind that, the standard errors here, right? They also speak to how many people are available to test certain points.
Yeah, it could be power issue.
So yeah, so the regions of this curve where there's fewer people, there's less power to detect those slopes and to compare those slopes against other regions. So.
Yeah, that clears it. Thank you.
Sure. All right, others. Okay, then I've got one more example to show you. This is not something I'm asking you to work on for homework 4, but it's another type of coding scheme that is useful for ordinal predictors in particular. Do you remember what ordinal variables are? Yeah, they are categorical variables where the options have a natural ordering to them, so they're not numbers. So experience 1 to 7 in your example for homework 4 is a case of this. So I'm on slide 37 in lecture 4 to show you an example. So I have a variable in the same data set where I'm predicting annual income from how happy someone reports that they are. And here are your choices. 1 is unhappy, 2 is neither, 3 is fairly happy, 4 is very happy, and 5 is completely happy. So are these really numbers? What do you think? I've got numbers on the x-axis, but are these really numbers? No. If you want to talk distances between them, is the distance between neither unhappy nor happy and fairly happy the same distance as the difference between very and completely? No, these aren't numbers. But you will see people pretend like they're numbers and fit a variable, for instance here, centering happy at 1, since that's the lowest value, and fit a linear slope through this. And so the slope estimate in this case is 0.74. So for every unit happier you are, your income goes up $700, and that's non-significant in this case. So whether or not a single slope makes sense for a variable in which these are not numbers, but they are ordered, that's actually an empirical question. So I wanted to show you how to set up a model that fits a separate slope for each transition point between these categories, because then you can test whether or not those slopes could be constrained to be equal and not hurt the model. So this is yet another coding scheme. Let me move this thingy out of the way here, to get at what's going to be adjacent categories. You will get a chance to practice this in homework 5. So this is another coding scheme. So I have happy as the original variable. 1, 2, 3, 4, 5 are the possible values that it takes on. And I am setting my model intercept reference point to be happy equals 1. So all of my new predictor variables, all 4 of them that I'm creating, are going to be zeroed out when happy equals 1. The object of this coding scheme is to have one variable that's the difference going from happy 1 to 2, another variable that's 2 to 3, a third variable that's 3 to 4, and a fourth variable that's 4 to 5. So these adjacent differences between levels of this predictor variable, that's what I'm setting up here. And so the way that it works then is very much like the other piecewise model, in that after you make the transition that the variable is trying to capture, it shuts off where you left off. And it's zeroed out before it's active. So to get from happy 1 to 2, I go from 0 to 1 on the first variable, and it shuts off. So if all I had was this first column in the model, what it would give me would be the one group versus the average of all the others, because all the others have a 1, if that's all I have. The second column then picks up to distinguish, to turn on, so to speak, between 2 and 3, and then it shuts off. The fourth column picks up at 3, and the third column picks up at 3, and the last column picks up at 4. So this is different than the dummy coding scheme that we did for the 3-group example in the extra 0 here down in the corner. So each of these contrasts picks up where the last one left off because of the 1s. It doesn't go all the way back to refer to the 1 group as the reference for these latter ones, the way that we did over here. So I'm going to have a question in homework 5 where there's 3 groups. You're going to be seeing whether or not fear of statistics predicts graduate school performance. That's homework 5, by the way, where there is low fear, medium fear, or severe fear. And I'm going to ask you to set it up this way so that you get the difference of low to medium and then the difference of medium to severe. So this is an alternative coding scheme to dummy coding if you want the adjacent differences rather than each group relative to the same reference group. So the means for happy then look like this. So here's the code that does this pattern. So I have the 0s and 1s in each here. And then here's what it would look like in a model where I put the 4 new columns in here, and I have differences between adjacent slopes. So I'm testing, for instance, whether the difference between 1 and 2 is the same as the difference between 2 and 3, and then the same for the other adjacent combinations. Here's what it looks like in Stata. So we have all of the separate statements replacing it. I'm using a little bit of conditional logic to shorten the number of statements necessary. So greater than or equal to 2, 3, 4, or 5. And then the 5 new predictors go in the model. And here's what comes back out. So first thing I would want to look at, the F up here. What is this F line on slide 41? What is that telling me? Big picture. Thumbs down. That's a very succinct way of putting it. Yes. So does happiness, does money buy happiness? Is that the phrase? Does happiness lead to annual income? Thumbs down. So more specifically, the 4 slopes that I'm putting in the model to distinguish these 5 levels of happiness, on the whole, do not result in a significant amount of information captured. So the p-value for the model is not significant, meaning the ratio of information explained to information unexplained is not good enough. And the effect size, we've accounted for less than 1% of the variance. So we do not have a significant prediction from happiness to income for the 4 slopes. And the individual slopes, as we go into the model results, so beta 0 is the expected income for somebody who says they're unhappy. They make about $15,000 a year. Beta 1 is the slope of this little line going from unhappy to neither happy nor happy. That acute difference from 1 to 2 in my ordinal scale is 1.69, not significant. Going from neither to fairly, also not significant. Going from fairly to very, oh, that's marginal. And then going from very to completely, also not significant. And so then the contrasts tell me whether these first 2 slopes are the same. Yes. The second and third slopes are the same. Yes. And the third and fourth slopes are the same, pretty much. So putting it all together, it looks like a model that has 1 slope in it would probably be sufficient because happiness is not related to income at all. But if you have a variable like this that's ordinal and it makes you squishy to fit a slope through it and pretend like it's a number, as well you should, this is what you can do instead. Squishy is another technical term. It means uncomfortable. So, like the feeling you get when somebody empties the toaster in your kitchen and doesn't clean up the crumbs and you step on all the crumbs. That face, Pam, exactly. You feel squishy. You're like, ugh, that's disgusting. So, ordinal variables treated as interval, that is disgusting. But very, very common. I have a lot of opinions, in case you hadn't noticed, but that happens when you're passionate about your work, right? Ragey, yeah, ragey for crumbs. Yeah, the people that I live with know better. So it's only when I visit other people that I would be stepping on crumbs from the toaster because the people I live with know better. All right. So, summary, putting it all together. What we've been working on in this unit is the idea that some predictors take more than 1 slope to fully capture how they predict an outcome. So that happens whenever you have nominal or ordinal variables that have more than 2 categories. That also happens when you're trying to capture a nonlinear effect of a quantitative predictor, such as through quadratic slopes or piecewise slopes. And in that case, we need that F section to tell us in a more general way, does that predictor and its set of slopes significantly predict the outcome? And then we can drill down into each slope and see what each slope does. So that's the story. All right, questions? So here's the code to go over what I just showed you in terms of happiness and how it does not relate to income and all that stuff. And as usual, in each little section here, I have words. So these are the words I would use in a result section to describe what I did. All right. Anything else before we call it a day? No? All right. Well, thanks for hanging in there. We've got a new stuff to do next week. Let me know if you need any help with homework or otherwise. Office hours at 3:15. So stay safe and stay sane. Bye, guys.